John B. Hagen, your textbook RF electronics. It's about the radio receivers. And to start, well, before let's consider some specifications, okay, for any kind of radio receiver, be it via and whether it doesn't matter if it is an AM receiver or an FM receiver or a television receiver. There are four basic specifications that need to be specified before you design the system for reception. So these are the gain. The first is the gain. Gain could refer to, it could be an RF gain. Okay, so this could be RF, or this can be this can be the audio signal gain. Okay, because you at the end of the reception, the modulation, you need to drive the speakers, for example. Okay, so you might need a class AB amplifier over there, so to provide the required amplification for the speaker. So gain could be for the audio application, it could be for the RF for the proper detection. Okay, so for example, look over here, and this is one of the earliest crystal set receiver. The first stage is a tuner. Okay, so it acts like a band pass filter. Okay, it might have a response like this, so something like this. So it's a band pass response. Let's say this FC is if you are considering this to be a AM receiver, then this FC for a typical AM broadcast range, which is from 550 kilohertz to 1700 kilohertz. So it is between 550 to 1700 kilohertz. So this center frequency is tunable. Okay, you see over here you have a tunable capacitor. Okay, so it also acts as a LC matching network for the antenna, right? Because antenna is picking all the signals nearby your FC. So FC for a typical AM broadcast, it could be 560. For a lower end of AM broadcast, it could be 1000, whatever. So you select the desired, or you tune the receiver to the desired frequency, which is desired for detection, and then you feed it through the diode detector. Okay, it's the same detection that we have considered earlier for the AM reception. So so you might want to have a stage after the tuning. You can have an RF amplification stage. For example, there is an RF gain over here. Why do we need to have an RF gain? Because for the diode, okay, so you might need a signal of few milliwatts over here for the diode to detect the envelope. Okay, so you might have a wave like this, a modulated AM wave could be. So it's a constant frequency but variable amplitudes like this. And what you are interested is in the you want to detect the amplitudes. So what you do is you employ a diode detector. So for example, this is the envelope. So the thing is, when in the negative cycle, when the diode opens, okay, this capacitor is going to discharge over a certain load, which is in this case a headphone or a speaker, whatever it is, and then it discharges with a time constant RC, and then it charges up again when the diode is conducting, discharges, charges, discharges, and that's how you're going to detect the envelope. Okay, so this is your modulating signal envelope that you're interested in, right? So by gain I mean you might need an RF gain, okay, for an appropriate level or a proper detection, proper diode detection before the detector. You need a RF amplification, and before you before you are going to send the signal to the load or the headphones, or you want to drive the speaker, you might want to have another stage for gain, and this could be your, let's say, a push-pull configuration of class B amplifier, or if you want to get rid of that crossover distortion, you might want to have a class AB amplifier. Okay, so these are again linear amplifiers, and you are not going to produce any unwanted harmonic content because it goes through the linear amplifier. So for a high fidelity signal, high high fidelity signal to drive the audio load, you might need a class AB or class A or class B amplifier. So you have two kinds of gains, RF and audio. Now then, another specification for the radio receiver is it's called the dynamic range. By dynamic range, it means, okay, that since the antenna is going to intercept a range of signals from, let's say, there's a weak signal and then there's a strong signal, and it refers to the level of the input signal that can be appropriately detected and demodulated by the receiver. And so, for example, if you have a certain noise floor, which is, for example, you have this noise which is being generated by the receiver itself, and you have a very weak signal that has strength which is considerable to that noise level. Okay, so let's say in the receiver you have a noise floor. Okay, so there's a noise floor like this, and you have a very weak strength signal. So there's a noise floor like this, and then you're having, let's say, a weak signal. This is your FM or audio signal, whatever it is. And then in nearby you have a very strong signal, okay, a very high peak that is easily discernible. The weakest signal, if that can be recovered, okay, so there is a range from weak to strong signal. So strong signal implies that you're referring to the strong signal handling capability of the receiver. So basically, it's the level of the signal that a receiver can detect and demodulate. Okay. And then you have the sensitivity and selectivity. Sensitivity, again, the lowest in the dynamic range that we're considering for any receiver. Sensitivity could be the lowest signal level that can be detected. So for a given noise flow, for example, this is your noise flow. This is the noise. So in the unwanted domain of noise, the weakest signal, which has a strength which is comparable to the noise level, this is your noise level, that can be detected, is the sensitivity. That's how much sensitive your receiver is. Okay, so that the lowest in the dynamic range, the lowest signal that can be detected refers to the sensitivity of your receiver. Selectivity is determined by the band pass limiting filter. Okay, so for example, over here you have a band pass filter. Okay. And what it means is that, for example, if you have a very high Q band pass filter, so selectivity is generally determined by the Q, or the quality factor Q of your band pass filter. If you have a very high Q band pass filter, that means the selectivity of the desired signal is high. So in a sense, we're going to reject all the other frequencies that are not desired. So if you have very high Q, your selectivity is high. Okay. So in other words, selectivity is determined by the band pass limiting filter, might be specified in terms of dB. So for example, 3 dB down at 2 kHz from the center frequency or the desired frequency, or 20 dB down at 10 kHz from the center frequency. So for example, if you have this band pass response, and let's say this FC is between 550 to 1700 for AM broadcast receiver, and you are somewhere over here, and so let's say you are down by 2 kHz. Okay, so this frequency is your this frequency over here is, let's say, FC minus 2 kHz. Okay, FC minus 2 kilo, and this level could correspond to from here to here, this corresponds to the difference could be, let's say, 2 dB. Okay, this is 2 dB. So with the difference of for those undesired frequencies which are at the difference of 2 kHz from your center frequency, the response goes down by 2 dB. Okay, you have 2 dB of attenuation. If even farther you are at, let's say, 20 kHz, right? So this could be from here to here. This could be 20 dB, let's say. Okay. So if you have a high Q or a narrow band pass filter, the shape of or the response of the band pass filter determines the selectivity parameter uh, of the radio receiver. Okay, the radio, if it is a high Q, if it is high Q, it's like this. Okay, so it's a very selective. I mean, at the center frequency. So this is your FC over here. So even if you are going to deviate from FC, very quickly the response falls. Okay, and this could be 30 dBs, 40 dBs, whatever. So if you're going to deviate over here, this is out. But anyways, this frequency or this frequency, response could be 30 dBs down. So high selectivity. High Q means high selectivity. Um, and sensitivity is determined by the noise power contributed by the receiver. So you're considering, again, for the sensitivity, you're considering the noise floor, okay, and how much a weak signal that has a strength comparable to this noise floor can be detected, and it can be demodulated by the receiver, determines the sensitivity. And usually this is specified as an equivalent noise power of noise power at the antenna terminals. So this is a self-powered crystal set radio receiver, and it's one of the earliest radio receiver employed self-powered crystal diode rectifier to recover the modulation envelope, okay, as we have seen before for the AM receivers, and it converts enough of the incoming RF power into an audio power to drive the earphone. Okay, so this is one of the earliest models, so you don't see any class AB amplifier over here for audio amplification or audio high fidelity purpose, any employment of those AB amplifiers. And similarly, you don't have any RF amplification stage over here, which is otherwise required in the modern radio sets. And but it's a basic structure again. So there's a simple LC tuned circuit, which the band pass filter to select. Again, you see it's with the band pass filter. There's determine the selectivity from the response of the bandpass filter. So the bandpass filter is required to select the desired station, and could also serve as an antenna matching network. So basically the power that you are going to transfer to the rest of the circuit of the bandpass filter, which is of course tunable, the power that is going to be transferred from the antenna, this LC section is going to match that power to the desired frequency. Okay, so it's also a matching network for the antenna. Okay, because that matching frequency is your center frequency. Okay? Other than that, there's no other frequency the bandpass filter is going to favor that to get through. Okay, so the considerations above show that a self-powered receiver can have a considerable range. Okay. But when a long wire, so what it says is that if you're going to, for example, you're going to have an inefficient antenna, or if you're going to replace a long wire antenna by a compact but a loop antenna. So if you're going to replace a long wire antenna by a loop antenna, and you're going to replace earphones by a loudspeaker, well, you need an amplification. Okay, so you need an amplification. So for an undistorted envelope detection of an AM signal, usually the signal applied to the diode detector must have a high gain. So before the diode detection, you need to have signal of at least 1 milliwatts of level, so the proper diode detection can be carried out. So the invention of vacuum tube followed by the transistor provided the needed amplification. So in vacuum tube type of receivers, you use vacuum tube to amplify the signals so that the diode detection can be carried out properly. Receivers normally contain both the RF and audio amplifiers. Okay, RF amplification provides enough power for the proper diode operation, while the subsequent audio amplification provides power to the loudspeakers. All right. Now we have tuned radio frequency, or commonly referred to as TRF receivers, and the first of the vacuum tube radios were TRF receivers, and they used a vacuum tube detector instead of crystal, and they added a RF. They have a pre-amplification RF stage and an audio post-amplification. So you can see over here, before the speaker, you have an audio amplification stage, which could be a class AB amplifier. Over here, you have an audio amplification stage, and then you can have multiple RF stages depending on the cascading of the bandpass filter. So these again are are tunable bandpass filters. Over here you see you have a tunable shunt and series LC elements that are going to select the center frequency, okay, depending on the Q of the those sections, which is the selectivity could be between any frequency 550 to 1700 kilohertz if this is an AM broadcast. So for the proper before the diode detection, if you're looking for the signal strength of around 1 milliwatt, so if you need a signal strength around 1 milliwatt for proper diode detection, you need an RF amplifiers. Okay, you need RF amplifiers. So you have both RF amplification and audio amplification in TRF receivers. So these TRF are tuned radio frequency receivers. Such they have an individual tuning adjustments for each of these several cascaded RF amplifiers. So you see there that is disadvantage of this configuration is that you have too many tuning stages. So for example, the changing stations, they require the user to adjust several dials, often with the aid of a tuning chart or a graph, before they key in or select the appropriate station. So this is a hypothetical TRF receiver with cascaded amplifiers and bandpass filters. So note that all the inductors and capacitors, they should be variable in order to tune to the center frequency. So it's not only the tuning of the center frequency of the bandpass filters, you also have to maintain a proper bandwidth. For example, in AM, it's 10 kilohertz. Okay, 10 kilohertz for AM. So the bandwidth of the this LC tunable bandpass filters, the 3 dB bandwidth over here at the point where the 70% response falls over here, this should be 10 kilohertz. Okay, so for AM applications, it's not only the FC we are going to tune, but the 3 dB bandwidth should be 10 kilohertz. Okay, so these are variable capacitors and inductors, right, to maintain the bandwidth and to for the center tuning of the bandpass filter as well. Then comes the Superheterodyne Receiver. So around 1917 and 18, we have this Superheterodyne Receiver. Heterodyne means mixing. So what you see over here, the difference between this configuration of a receiver and this configuration is that you have a mixer over here with a local oscillator. Okay, so what's going to happen is that you're going to have a fixed tune circuit before, and then you're going to mix it up with the local oscillator frequency, and this frequency is going to produce new frequencies after mixing. So we'll call this the output of the mixer is IF, intermediate bandpass filter, where the amplification and other processing goes on. And then you have the detection. So the disadvantage of the previous TRF receivers such was that was the cost and the inconvenience of having many tuning adjustments. Okay, so you can see that over here there are many tunable filters, and you have to tune. You have to maintain the bandwidth, and you have to tune the center frequency for a large number of cascade stages. So most of these adjustments were eliminated with the invention of the Superheterodyne Circuit by Edwin Armstrong in 17. So that was World War I times. So Armstrong circuit consists of a fixed tune. It means single frequency TRF back-end receiver preceded by a frequency converter. So the front end, once after the tuner, you have a mixer stage with a local oscillator. So you have a mixer and local oscillator so that the signal from the desired station can be shifted to the frequency of the TRF backend, and this is called the intermediate frequency, or IF. Okay, so what happens is, look, you have a once you select the center frequency equal to, let's say, well, let's call this a desired RF frequency. You have a desired RF frequency over here. This is going to be mixed up, and this mixer, by the way, it could be a balanced diode ring mixer, okay, or it could be a non-linear diode mixer, it could be a JFET mixer, whatever, right? It could be a Class C mixer as well. So here we have, if your FI is 455 kilohertz, which is typical of the modern receivers. For AM applications, the intermediate frequency is fixed, 455 kilohertz with 10 kilohertz bandwidth for AM. Here you see you have FRF, the radio frequency, plus the local oscillator frequency is FRF plus FI, the intermediate frequency, okay, and this is my FLO, local oscillator frequency. And if you can guess what the output of the mixer will be, well, the output will consist of sum and difference of the frequencies, and you can see the difference is Fi. Okay, the sum, however, will be, what is the sum? Sum will be 2. Okay, I'm going to write the sum over here. 2 FRF, 2 FRF plus Fi. So we don't work with this high frequency. We need the intermediate frequency. Okay, so whatever the station you are going to tune in, okay, this tuner is going to tune in. It is going to be mixed up with the local oscillator frequency, that is RF plus FI. Okay, FI is 455 kilohertz, for example, for the FM, and whatever the station you're going to tune in, it's going to be converted to FI. Okay, and then whatever the band pass filtering or amplification is going to be needed, it's going to be done in this IF stage intermediate. Okay, so there is an IF amplifier before the detector to give the detector an appropriate level of input signal for envelope detection. Okay, and then after demodulation, of course you have the audio amplifier to run the speaker. Okay, so Superheterodyne circuit is still the circuit used nearly for every radio, television, and radar receiver. So, for example, if you are going to use this for FM, then this IF frequency could be 10.7 megahertz. If you're going to use for television, the intermediate frequency could be 45 megahertz because of large bandwidth requirement for television transmission. So, again, over here, the selectivity is provided by a fixed tuned bandpass filter. So selectivity, one can say, is again, it's depends on the quality factor of the bandpass filter, the selectivity, how much it is able to reject, the capability of bandpass filter, the response, such that it can only let through the desired frequency and reject all the others, is selectivity. Selectivity is provided by the fixed tuned bandpass filter in the IF amplifier section. Okay. So we have this IF bandpass filter that is going to provide the selectivity in the superheterodyne receiver. And then you have the AM detector, which is still a diode, and this is the basic envelope detector. And all the RF gain can be contained in a fixed tuned IF amplifier. But this idea is not much popular. You will see that later, that there's sometimes there are reasons for having some amplification ahead of mixer as well. Okay. Just to give you a rough idea, what happens is, why do you need another bandpass filter before the mixer, ahead of mixer is? So let's consider this frequency over here to be, what if this frequency is FRF plus twice of Fi, okay, and if your local oscillator frequency is as such, so what I'm saying is, instead of FRF, you're going to tune into a frequency, because antenna is going to transmit all the frequencies. Okay, and although your tuner is giving you FRF, which is tuned to FRF, but still we need a bandpass filter ahead of the mixer, such that if such a frequency shows up over here, then the difference of this frequency with the local oscillator frequency over here, you see, is again Fi. Do you understand that? You see, this FRF is going to cancel, and then you have the difference is again Fi. So that means for FRF plus 2 Fi, and FRF. For these two different frequencies, the intermediate frequency is the same. Okay. If the intermediate frequency is the same, then the demodulation or detection is going to give you well, a different audio for because the two frequencies are not the same, but the detection has occurred so that it has picked up by the receiver in the same IF stage. Okay, but the frequencies are different, so you're going to hear different information from here, so different audio from the speaker. So we call this frequency to FRF plus 2FI as the image frequency. Okay, so for let's say for rejection of the image frequency, we need a band pass filter. Okay, so what this this statement is implying is that, okay, so all the RF gain is contained in the fixed tune IF amplifier, although we will later see that there are sometimes reasons for having some amplification ahead of mixer. So the reason is that if you can employ a band pass filter as such, and if this is your FC, which is tuned to FRF, which is the desired frequency, and we are not looking for a frequency that is higher than FRF. Let's call this the image frequency. Okay, so we have this image frequency somewhere over here. This frequency is, let's say, FRF plus twice of Fi. So let's say we drop the response over here from here to just require the frequency plus the response. It can be minus, let's say, 30 or 40 dBs. Okay, so let's say minus 30 dBs. So we are going to get rid of this frequency. We're going to get rid of this frequency, and we're going to pass the RF component only. Okay, so not the image frequency. So that's how you can employ a band pass filter ahead of mixer to get rid of the image frequency. So the Superheterodyne receiver also serves as a block diagram for the FM broadcast, where the IF is 10.7. For television, I've already told you this is around 45 megahertz.